Hey, we're going to start our new unit on energy. Let's go ahead and start off with what is energy and how is it measured? Turns out what energy is not the easiest thing to explain, but we don't really have to worry about it too much, okay? So let's just say, for the sake of our class, that energy is basically the ability to move things, to make things happen, to heat things up, to make electricity, whatever, okay? So it can take lots of different forms. That's what's a little bit tricky about it. So energy can take the form of a moving object. It can take the form of random atomic motion, which makes things hot. Sound is a form of energy in the form of back and forth molecular vibrations. Light is a form of energy. Electricity is a form of energy. It has many different ways of looking, but ultimately, what we need to concern ourselves with is this. As a society, at least from an environmental science standpoint, what we mostly do is we look for forms of what we call stored or potential energy. So there are some ways in which energy packages itself in a way that it can be stored for a long period of time and then released later. The three most commonly encountered forms of potential energy that we'll come across are chemical potential energy. And what that basically means is energy can be stored in the bonds between atoms in different chemicals, right? So gasoline has a lot of chemical potential energy. Carbon dioxide and water molecules do not have many chemical potential energy. Batteries have chemical potential energy, coal, oil, natural gas. These are all things with a lot of chemical potential energy, which are really important in terms of how humans power our society. There's another way we access it, which is gravitational potential energy. Anything that's in a position where it can fall will release gravitational potential energy and turn it into energy of motion, which we call kinetic motion or kinetic energy. But in terms of the our science that we're looking at here, environmental science, we're mostly talking about water stored behind a dam has gravitational potential energy, and as it moves down to a lower level and comes out the bottom of the dam, it's converting that gravitational potential energy into what we call kinetic or motion energy, which then generates electricity. And another form of potential energy that we deal with in our society is nuclear potential energy. So uranium 235 is an isotope that has a lot of potential energy stored between the neutrons and protons in the nucleus. And especially because it's one where we can actually release that energy. All nuclei have this energy, but most of them there are in a, a form that can't be released. But uranium is one of the rare cases where it can. All right, now let's just get on with it because there's a lot to cover here. So, all forms of energy, whether it's potential energy, in a battery, motion energy in a car, sound energy, light energy, I don't care what it is, we measure it in units called joules. Okay, and let's not worry about what a joule actually is. Okay, that's more of a physics question, but let's just say that's what we measure. And so, the one thing you do have to know is societies are large, and there's a lot of people using a lot of electricity. So the units that we use are sometimes larger units. So we often talk in terms of kilojoules, which is 1,000 joules. You need to know that. You need to know 1 kilo equals 1,000 joules. You need to know that 1 megajoule would be 1,000,000 joules. It's kind of easy. Mega million, right? Okay. A gigajoule or gigajoule, I always call it gigajoule. I'm not sure what you're really supposed to call it. But a gigajoule is a billion joules. And then a terajoule would be a trillion joules. Okay. And so you should know these numbers. Okay. You should be able to convert between these because they do get used and sometimes they want you to convert. So it's one of those things where this course does ask you to memorize a few things. So let's get on it. Now, it's pretty important to understand the laws of thermodynamics, at least the first two. And you probably already do. And I think we've already talked about them a bit, but let's do it again. So, a very important idea in energy is the first law of thermodynamics. And what that says is basically, you can phrase it different ways, but energy can never be created or destroyed. In other words, every joule of energy that's there, it has to come from somewhere and it has to go to somewhere. It didn't just come into being and it didn't just disappear from existence. All the energy comes from somewhere and goes to somewhere. There's no exceptions. Okay. So another way of saying this is we can't make energy. What we can do is we can find it in one form and convert it to another. But we can't make it. We can just find it and use it. Now, let's just take a look at how this would come, this first law of thermodynamics would come to play in terms of electrical generation. Okay. So, coal is a typical substance that we use to release chemical potential energy to run our society. It's the main substance with which we power modern society, unfortunately. So, when I burn it, basically what I have is let's just say a chunk of coal has 10,000 joules of chemical potential energy in it. Okay. So, we say it has 10 kilojoules of potential energy in it. When I burn it, what I'm basically doing is I'm reacting with oxygen and I'm converting it into carbon dioxide instead of pure carbon. And it turns out that carbon dioxide has less energy in it. All right. And so what happens is that 10 joules of potential chemical energy gets turned into 7 kilojoules of heat and 3 kilojoules of light. When you sum this up, you still come up with the original number, 10. We never create or destroy energy. We just simply turn it from one form to another. Okay. Now, so let's just, okay, so how about this? Where did the energy in coal come from? All right, let's just work through this real quick. Okay, so let's just start with you. All right, so basically, coal comes from trees, ancient trees. We've talked about this before. So trees get their energy basically from the sun. So let's just go all the way back to the sun. So basically, the sun is a star, and what stars do is they take hydrogen, which is the most early primordial form of matter. And matter, if you remember E equals mc squared, matter and energy are the same thing. Matter is just one manifestation of energy. And so what stars do is they basically convert hydrogen to helium, and that releases nuclear potential energy left over from the formation of the universe. And that gets converted from nuclear potential energy into heat, which is usually what happens with nuclear potential energy. Now that heat gets converted into light energy. Hot things give off light. Okay, that light travels through space and reaches the tree on the surface of the Earth. That tree then takes that energy that was originally nuclear potential energy of the sun, got converted to heat, got converted to light. Now it takes that energy and uses it to turn carbon dioxide and water, which have little amounts of potential energy, into glucose, which has a high amount of chemical potential energy. So basically, we took that energy and we turned it into chemical potential energy. The tree died 300 million years ago, fell into a swamp, could not be consumed by bacteria. Heat and pressure eventually turned it into coal, but the chemical potential energy is still in there. So essentially, coal has chemical potential energy that was captured from sunlight 300, 400 million years ago, just sitting there. Then we take that coal, we put it in a power plant, we convert it into heat, and then we turn that heat into electricity and we send it to our home. So that energy always has to come from somewhere and go to somewhere. That's what the first law of thermodynamics tells us. Now, let's talk about electricity in particular, because electricity is a really, really useful form of energy, and here's why. It's really easy to convert electricity to other forms of energy. It's really hard to convert other forms of energy to anything else, honestly, other than to heat. So, for instance, you can turn electrical energy into light with a light bulb or an LED. You can turn it into sound with a stereo or a speaker of some sort. You can convert it into motion with an electric car or a blender or a drill. You can convert it into heat with a space heater plugged into your wall. You can charge up the battery in your phone and turn it back into chemical potential energy. You can transform into gravitational potential energy by lifting something up with a crane, escalator, elevator. You can even turn it into nuclear potential energy in rare cases using a particle collider, right? They're electrically generated and you slam atoms together. So the point is, electricity is this really desired form of energy because it's so easily transported and transformed. It's golden, and our whole civilization is based on it. Now, it turns out though that of all the forms of energy, the hardest one to make use out of is heat energy. So we often think, because heat is just random atomic motion, and random is kind of hard to do anything with. Now, it's possible to do it, and we'll talk about this, but basically it's difficult to make heat do anything. So we often think of heat energy as lost energy or waste energy. Remember, energy is never destroyed, but once it gets converted to heat, it's very difficult for us to do anything with it other than make ourselves warm. Okay, it's very difficult to convert heat energy into anything other than what it is. Now, this brings us to the second law of thermodynamics. Now, the second law of thermodynamics can be stated lots of different ways, but I think the best way to wrap your head around it is to say this. The second law of thermodynamics tells us this: anytime energy is transformed from one form to another or transferred from one object to another, some of it will always, full stop, be converted into heat energy. You will always lose some to heat. All right. So, for instance, if I put a battery in a toy car, I have 10 joules of chemical potential in this battery. The first law of thermodynamics says you could never get more than 10 joules of kinetic or motion energy out of it. Okay. But the second law of thermodynamics says, well, you know what? This is not possible because some of that energy that was here is going to end up as heat. So this is possible. I start off with 10 joules of chemical potential energy in the battery, and I end up with 8 joules of kinetic or motion energy and 2 joules of heat energy. I still am obeying the first law. 10 joules became 10 joules, but I'm obeying the second law. some heat energy had to be produced. It's unavoidable. And this brings us to a really important concept they're definitely going to test you on, and it's the concept of efficiency. Because efficiency is going to be really important in order for humanity to get out of the situation we found ourselves in terms of our energy dependencies. So efficiency is essentially is the percent of energy that we end up with in the form we want of the type we started with. So basically, if I take the amount of expended energy, how much coal I used, and I put that in the denominator, and I take the amount of energy I wanted, electricity, and put it in the numerator, that gives me a percentage, right? And so for instance, let's look at a car, okay? So let's say a car converts 400 joules of chemical potential energy in gasoline, and in doing so, it produces 100 joules of motion energy, which we call kinetic. Uh, and the remaining 300 joules just go to make the car hot, to make the sound of the engine and the tires and so on, right? So what's its efficiency? Well, the total input energy or expended energy was 400 joules. So that's what I'm going to put down here. The output energy that I wanted was motion, and I only got 100 joules of that. Now, remember, the energy never got created or destroyed, right? But when I talk about efficiency, it's how much of the energy that I wanted did I get compared to what I started with. So in this case, 100 divided by 4 is 0.25. I have 25% efficiency, which I'm sorry to tell you, people, that's pretty typical for cars. Think about that. Only 1 out of 4 joules of the energy we put in a car actually goes into making the car do what we want. All right. So another way of phrasing the second law of thermodynamics is to say you can never have 100% efficiency in any energy conversion system. There's always going to be some quote loss to heat. So let's look at another example. Okay. So each kilogram of coal has 300 megajoules of chemical potential energy stored in it. That's a lot, right? Okay. Now, in each second of operation, my coal-fired plant is going to burn 12 kilograms of coal. And in doing so, it's going to produce 150 megajoules of electricity. So what's the efficiency of this power plant? By the way, these are real numbers, okay? So the first thing I'd have to do is I'd have to figure out, well, how much expended energy was there? What was my input energy, right? So my input energy would be I have 12 kilograms of coal, and each kilogram produces 30 megajoules. So that gives me 360 megajoules of input energy or expended energy. And that's what I'm going to put down here. That's what I used to get what I got. And what I got was my output energy or intended energy, which was 150 megajoules. And so when I divide this out, I have to be careful to make sure these units match up. I can't divide megajoules by kilojoules, right? And what I get is 41% efficiency, which is typical of a modern coal-fired power plant. Again, more than half the energy that we release is just going to make the coal plant hot. It's not doing us any good. So improving efficiency is a really important idea in order to extend the duration which fossil fuels are going to last, because we're going to run out of them, and also to reduce the rate at which we're putting carbon dioxide in the atmosphere by burning these fossil fuels. So improving efficiency is really important, and I've seen tremendous improvements in it in my lifetime. The biggest one being LED lights. So when I was a kid, it was all incandescent bulbs, and when you touch them, man, they burn your hand, which means they're generating a lot of excess heat, right? So these LED lights are 75% less energy usage than a conventional bulb. So they're far more energy efficient. Electric cars are becoming more and more common now. The thing about an electric car is, the engine doesn't get hot like a regular car does. So right there, you're not wasting all that energy. And when you put your foot on the brakes, instead of making the brake pads hot, you're doing that a little bit, but you're also causing the car to convert kinetic energy of motion back into stored energy in the battery in the form of chemical potential energy. So you're not wasting energy as heat. You're saving it. Okay, you're conserving it. Another important idea they want you to know about in this course, and it's kind of cool, is called cogeneration. So cogeneration is basically a way of improving the efficiency of power plants, and essentially it just means this: take the quote waste heat of the power plant. Remember, those power plants are only 41.7% effective, which means essentially you've got like 58% of the energy is wasted heat energy, right? So what do you do with that wasted energy? Well, one thing you could do with it is heat is good for one thing, it's good for heating, right? So you could heat buildings. You could use that heat to help offset the costs of industrial processes, heat office buildings, and so on. So that's what we mean by cogeneration. It's definitely something they're going to quiz you on. Um, Let's see here. What just happened? Oh, okay. Yeah, yeah. Oh man, what's going on here? Okay, all right. Man, I'm sorry about this. I'm lagging here. This is terrible. Okay, so this is embarrassing. Okay, so here's what a typical coal-fired power plant looks like, right? I put coal in, I burn the coal here, I generate heat, I bring water in here, and and we'll get into this later. But the way you make electricity out of heat energy, random motion, is you make steam. I boil water into steam, and then I use the steam to turn a propeller-like device called a turbine, and that turbine spins a magnet through a coil of wires, making electricity in a thing called a generator, and then that goes out to your house, right? But that 52% of leftover energy typically just goes here, and I basically have to cool it down before I release it in the water so I don't harm the aquatic ecosystem, something we'll talk about later in the year. But with cogeneration, what we're going to do is this. Instead of taking that, they're saying 60 to 70%, okay, but whatever, okay. Instead of just sitting it out to the tower to cool off, I'm going to make my electricity, right? 30 to 40% useful electricity. But then I'm going to take the other with cogeneration, and I'm basically going to use that. Not a very good diagram. I'm going to take that energy and I'm going to use it to heat homes and do other things, which people would have otherwise been burning fossil fuels to do. So it does make a lot of sense. So now in designing where to put power plants and other office buildings and things like that, they take into account cogeneration in an attempt to try to reduce the amount of energy we're wasting, which is really wise. Okay, now buckle your seatbelts because we're not done yet. Power. This is a term we always hear, power, right? Well, here's what power actually means. Power is the rate at which we convert energy from one form to another. Yeah, it's the rate at which your car converts gasoline into motion, right? It's the rate at which the company converts coal into electricity. So the unit for measuring power is the watt, W. I'm sure you've heard of watts, okay? Watts just means 1 watt means you're converting 1 joule of energy every second from one form to another. So 1 watt just equals 1 joule per second. You need to know that. Put that one up here. Okay. So therefore, a 100 watt light bulb, which is typical when I was growing up, a 100 watt light bulb basically converts 100 joules of electrical energy into other forms, light and mostly heat, unfortunately, every second. So 100 joules every second of electricity is being converted into other forms. That's what we mean by 100 watts. Now, typical coal. So in terms of providing energy to municipalities, we need to talk in terms of how many joules per second are we going to give them. So just so you know, a typical coal-fired power plant produces about 600 megawatts, so 600 million joules per second is coming out in those wires as electrical energy. All right. Now, a typical wind turbine, which you start to see more of in Korea and other places, it only produces about 1.6 megawatts, and that's under optimal conditions. Right? So you can see there's quite a big difference there, right? Uh, and then a typical nuclear power plant can be quite robust, and it can produce up to a gigawatt. So in other words, like a billion joules per second of energy can come out of these things. Now, I'm sorry to tell you this, but if you were to look at your family's power bill, here's what you're going to notice that you're really paying for energy. You're not really paying for the rate or power. We call it the power company, but honestly, you're not paying for power. You're paying for joules of energy, right? But instead of charging for joules, you use a lot of joules and you have this big number, and people don't like big numbers. People don't want to look at their bill and see scientific notation. So what the power companies came up with is, was I think, kind of a stupid idea, but you got to get used to it because it's definitely on your test. They said, you know what? We're going to charge people by the kilowatt hour. Okay. Well, it's just joules. Okay. I'm going to show you what. The bottom line is this. Get this into your head. A kilowatt hour is not a measure of power, it's a measure of energy. It's just another way of repackaging joules. How many joules? Well, to be precise, 3,600,000 joules. You should just memorize that number. Okay. It's going to be useful on the test. Why does it get that? Well, here's why. Because 1 kilowatt is 1,000 joules per second of energy conversion. 1 hour is 3,600 seconds. So therefore, 1 kilowatt hour is 1,000 joules per second times 3,600 seconds, or in other words, 3,600,000 joules. And I think that's it. Okay, thanks for watching. I hope this wasn't too long.